All right, Joe. Let's do this. 3.3 properties of functions. Okay. So we'll learn more characteristics about functions. We'll go over even and odd functions, intervals of increase, decrease, constant, max and mins, what a secant line is, all that great stuff. Okay. So first we start with even and odd functions. What does it mean to be an even function? A function f is even if and only if, whenever the point xy is on the graph of f, then the point negative xy is also on the graph of f. So let's look at a graph to see what that actually means. So if you are an even function, then graphically, you are symmetric about the y-axis, which would be the first picture here. And if you are symmetric about the y-axis, then what that definition said is if you have a point xy, and if you are an even function, then if you're symmetric about the y-axis, there should be a point negative xy when you flip it over. That's all that says. Okay. So this is what it means to be even graphically. To be even graphically, you are symmetric about the y-axis. Okay. And then, algebraically, a function f is even if for every number x in its domain, the number negative x is also in the domain. So if you want to check algebraically whether or not you have an even function, all you have to do is plug in negative x for every x, and if it returns to you the original function, this means you have an even function. Okay, and maybe we can see what that looks like. I'll go to the next page and let's try it out. Like number one, let's try it on number one. All right, so we're gonna say f of negative x, which means we plug in negative x for every x. So this will give me negative x squared minus 5. Okay, now just simplify it and we get f of negative x, and remember that negative x squared means negative x times negative x, which is positive x squared. So we get x squared minus 5. So what we have just done is plugged in a negative x, and the outcome was the original function. So this means that since we got f of x back, this function is even. That's it. Okay. So that's how you check algebraically if a function is even. Plug in negative x for every x, and if you get the original function back, it is even. And trust me, even and odd properties will follow you in pre-cal and will follow you in calculus. So just remember these. Okay. So back to the first page. So there we have an even function. Now we have an odd function. If your function is odd, then if there's a point xy on the graph of f, then the point negative x, negative y is also on the graph of f. So what does that mean graphically? Well, let's look. To be an odd function means you are symmetric with the origin. Where is the origin? The origin is always known as 0, 0, right? The origin. It's always 0, 0. Okay, but what the definition says is if I have a point xy, and my function is odd, then graphically, it's symmetric about the origin, which means it'll flip over the origin, and I'll get my point negative x, negative y. That's it. So to be odd means you are symmetric about the origin. Okay. All right, so that is odd, and that is graphically. Now, to check for an odd function algebraically, you do the same thing as if you were to check for an even function. You take negative x and plug it in for every x. And if the outcome is the original function, but negative, meaning all the signs have changed, then you have an odd function. Okay. So again, we can go to the next page, see what that looks like. Who's going to be odd? Oh, yeah. 3 will work. Okay. So we want to check to see if it's odd. So we plug in negative x, which means I'll get 5 times negative x cubed minus negative x. Okay. And then simplify. I'll get negative 5x cubed, because once again, that's negative x times negative x times negative x, which gives me negative x cubed. Okay. And then plus x. All right. So what we get back is negative 5x cubed plus x. So remember, to be odd algebraically, all the signs must change. So compare this answer to the original function. In the original function, that 5 is positive, and here the 5 is negative. That x is negative, this x is positive. Have all the signs changed? Yes. Which means that this gave back to us negative h of x, which means this is an odd function. And also, one quick way to check if it's odd, like if you are still wondering if it's odd, all you have to do is take negative 1. Oops. So I just call this a quick check. Take negative 1 and multiply it by your original function. Well, basically what the definition says, right? And I'll have negative 1 times 5x cubed minus x. And that'll give me negative 5x cubed plus x. Does this look like that? And it definitely does. So that is one way to check if it's really odd, if you're second guessing yourself. Okay. Okay, back to the first page. So now we know even and odds, another part of the theorem, and I said it while going over what even and odd meant. A function is even if and only if we are symmetric with the y-axis, which is the first graph. This is even, right? Even. And then a function is odd if and only if it is symmetric with the origin. This guy, symmetric with the origin. This is odd. And then if you are neither symmetric with the y-axis and not symmetric with the origin, then you are considered neither. Neither, neither, either, either. Yeah. All right. Neither. Okay. So that's even and odd functions. Let's go ahead and finish the next page. So here we want to determine, are these functions even or odd? And if they're even, say what they're symmetric to. And if they're neither, or if they're even or odd, say what they're symmetric to. If they're neither, nothing. Don't worry about it. Just say neither. Okay. So for number one, we did it already. Since we're even, we are symmetric with the y-axis. Okay. 2. Do it. G of negative x. So we're just, again, algebraically checking if these are even or odd. And you'll get negative x cubed minus 1, which will give me negative x cubed minus 1. Did we get back the original function? Did we get back this function? No, so it's not even. Did we get back the original function, but all the signs have changed? Which means if this was positive, it's now negative. That's a check. But now if this is negative, this should be positive, which not a check. So not all the signs have changed, which means this one is neither. All right. Moving on. We did this one already. It was odd, which means it is symmetric with the origin. Okay. And moving on. 4. All right. So again, check f of negative x gives me the absolute value of negative x. Okay, well, we know the absolute value makes everything inside positive, right? But we have to do this properly. So what I'm going to do is just extract, pull out that negative 1. So we're going to get the absolute value of negative 1 times the absolute value of x. All right, and there's a reason for this, because if we just said, all right, like we normally do, the absolute value of negative 5 would be 5. Well, it would be wrong to say the absolute value of negative x equals positive x, because if we're looking for even or odd, does this look like the original function? No. So the absolute value just can't disappear like that. So this is why above we are doing it properly. And now we know that the absolute value of negative 1 is going to be 1. So you get 1 times the absolute value of x, which now brings us back to the original function of the absolute value of x, which is the original function, which means this is even and is symmetric with the y-axis. Okay, perfect. Last one, rational functions. All right, these ones are a little tricky. And we'll do the same thing. Plug in negative x. I get negative x over negative x squared minus 1, which will give me negative x over x squared minus 1. Now, look at it. Did we get the original function back? And that answer is no. That's a negative x, that's a positive x. But then, did we get the function back, but all the signs have changed? Here's an x, there's a negative x. That's good. Here's an x squared minus 1, there's an x squared minus 1. No signs have changed there. So we can say it's not odd. But there's a reason why I said these are tricky. And this function is actually odd. But in order to prove that, you must do the check that we did above earlier. Because if we do the check, we say take negative 1 and multiply the original function, which means I get negative 1 times x over x squared minus 1. And the way we multiply this is that this negative 1 just multiplies that x, right? So this would become negative x over x squared minus 1, which makes us think, does this look like that? And the answer is yes. So this function is definitely odd. But again, always check on rational functions. Because when we say odd, we want all the signs to change. But since this is a rational function, only the sign in the numerator has changed. So it is always a good idea to check. Okay. And since it's odd, it is symmetric with the origin. Okay, excellent. Those are even and odd functions. Now we get into the definition of intervals of increase, intervals of decrease. So the first one, a function is increasing on an open interval I if, for any choice of x1 and x2 in this interval I, the value of x1 will be less than x2, and the value of y at x1 will be less than the value of y at x2. What does all that mean? Well, let's look at it. Zoom in, right? So we'll say here, for your increase interval, so just keep it simple. Here is x1, here is x2, and if we're increasing, our graph would look something like this. And by definition, here I'll plot some points. This is f of x1, this is f of x2, and by definition, it said x1 is less than x2, which is true based on my graph, right? If x1's to the left of x2, then x1 is definitely smaller than x2. And then if we're increasing, the other part said that f of x1 would be less than f of x2. So that's all that says. That's it. And this is how you find an interval of increase. Okay. Two, a function is decreasing on an open interval I if for any choice of x1 and x2 in this interval I, with x1 being less than x2, we have that the value of y at x1 is greater than the value of y at x2. So once again, what does that look like? And we can come this way. So once again, plot it, x1, x2, and if we are decreasing, we would look something like this, where again, here's f of x1, f of x2, and by the definition, x1 is still less than x2, but the y value at x1 is greater than the y value at x2, which is all shown here. All right. And the last one is a function is constant on some open interval I for all choices of x and I, the values of y are equal. Okay. So to represent being constant, here's x1, here's x2. There's my constant graph. And what this says is that f of x1 and f of x2, if our graph is constant, then these y values are equal. That's it. Okay, cool. So that's what intervals of increase, decrease, and constant are. So let's try it out. We are going to be given a graph, and we want to obtain information from it, just like we did in 3.2. So for this one, it says, find any intercepts, x-intercepts, y-intercepts. So for x-intercepts, I have negative pi 0, 0, 0, and pi 0. My y-intercept, which is on the y-axis, is again 0, 0. Okay, and then B, find the domain and range. Okay, so domain, once again, deals with x values. And the smallest x value that we start with is negative pi. And the largest x value that we end with is positive pi. And then range is the y values. So once again, start with the smallest y value, which is at negative 1, and end with the largest y value, which is at 1. C. Find intervals of increase, decrease, or constant. So I'll shorten it up. There we go. Increase, decrease, constant. Okay, and the way we find these is we read the graph from left to right. And when we state intervals of increase or decrease, we always state and only state x values. We never ever state y values. So looking at the graph on the left, from negative pi to negative pi over 2, right? From this stretch of graph, it looks like the function is decreasing, right? The function's decreasing. So we'll say that from in the decreasing part, negative pi to negative pi over 2, the function is decreasing. And then, after negative pi over 2, what's the function doing? It's starting to increase. And this function increases from negative pi over 2 to pi over 2. So negative pi over 2 to pi over 2. And then last, starting back at pi over 2 and ending at pi, we see that my function again begins to decrease. So from this stretch of numbers, we decrease from pi over 2 to pi. And there are no intervals of being constant, so none. Okay. Quick word of caution for my math lab. Some new update out there, or somebody new, I don't know. Something happened with notation. So for years and years, intervals of increase or decrease have always been in parentheses, no matter what. And the reason they're in parentheses is because they're not domain and range. They're not stating where the function exists. They're stating where you increase and decrease. Domain and range get brackets or parentheses because it's stating where the function lives. Increase or decrease should always get parentheses because it's just where's the function increasing, where's it decreasing. But now, out of nowhere, we were blindsided. If you're going to state this in your homework, all of your intervals of increase and decrease must be in brackets. I don't get it. And I could make an explanation up for it, but that would just be helping them out. So it should always be parentheses, but when you put your answers in my math lab, it's gonna need brackets. So just word of caution. Let's say MML answer. Times are changing out there. And I get it. I mean, maybe it's because the points exist, like the points are defined. So if you're going to state a defined point, yes, you'll use a bracket, but it should always be parentheses. Maybe I'm just an old dog who doesn't want to learn that new trick, okay? All right. So if you type parentheses in my math lab, it's going to be like wrong, so use brackets. Unless it changes, let me know. But it's even in the new book too. They changed all the notation in the new book. So mind-blowing, y'all, mind-blowing. All right, and D, is this function even or odd? Well, it's certainly not symmetric about the y-axis, right? If it was symmetric about the y-axis, I could take this point and have almost the same point over here, negative pi over 2 and 1, right? It would flip right across the y-axis. So it's not even, but then, is it odd? Which means if I take this point and flip it over the origin, I should get the same point, but everything is negative. Or you can even say, I take this negative point, flip it over the origin, and I get the same point, but everything is positive. So this is definitely odd. Okay. Let's do it again. So for this guy, first off, find x-intercept y-intercept. And for x-intercepts, looks like I have one right there. 1/3 and 0. And then right here, which is not clearly stated, but I'm going to say 2.5 and 0. Or 2.5 is also known as 5/2 and 0. Okay. And then for my y-intercept, right there on the y-axis, 0, 1/2. All right. B. It was domain and range. Okay. Once again, domain starts with the smaller number. I want to move myself. Let's see. Yay, I'm down there now. Okay. All right. This would be fun when I move myself. I can point. That point's right there. Right there. Okay, cool. Now I gotta learn. Maybe for next time. That'll be great. Okay. So we start at the smallest x value, which is -3, and we end at the larger x value. Oh, it's right above me. I can do that now. Ooh, at 3. Yeah. All right. Okay. Too much fun. All right. And then range. Start with the smallest y value, which looks like the lowest we go is -1. Right there, right, -1. And then the largest y value we go up to is 2. Yeah, 2. Perfect. And then C, increase, decrease, constant. Okay. And we read the graph from left to right, and remember we only state x values. So looks like from -3 to -1, our graph is pretty constant. So -3 to -1. Maybe I should put brackets. I'm not. I'm a rebel. This change is not good. All right. And then from -1 all the way down to 1, right? So from this x value to that x value, the function is decreasing. So we say from -1 to 1. Okay. And then increase, I'm not even reading it. Let's see. And then from 1 to 2, we remain constant again. So from 1 to 2, we are constant. And then from 2 to 3, we increase. Hey, look at that. And then D, even, odd, neither. Put myself there, right? Does this graph reflect across the y-axis? No. Does this graph reflect across the origin? No. Right? There is no symmetry at all, so this is neither. I'm going to be more interactive like this now. See? New things pop up every now and then. All right. Yeah. All right. So that's intervals of increase and decrease and constant. Everything else we've known now. Domain, range. Now we know symmetry, even or odd. Lovely. Okay. Next is a definition on a local maximum and local minimum. So a function f has a local maximum at some value c if there is an open interval in I containing C, so that for all x in this open interval, we have that the y values of x are less than the y value at C. We call f of C a local maximum. What does all that mean to us? Nothing, because did it make sense? Probably not. Okay. So to show you what this one is talking about, so let's say I have an x value at some number C, right? An x value at some number C. Then my graph looks something like this, right? Okay. Well, what we're saying is that at this x value of C, there exists a y value at this x value of C. So f of C is the y value at C. And at this point, it is one of the high points of the graph, because what it's saying next is that all the other y values leading up to it are smaller than the y value at C. So this would be f of x, f of x, f of x. And by the definition, it says all the other values of f of x are going to be less than f of C, which means f of C is your local maximum. That's it. And even if you fell down this side, that would be f of x, f of x, f of x. And all it's saying is, once again, is that these y values and these y values are smaller than the local maximum's y value. That's it. Okay, which means that brings us to the next definition of a local minimum. You have a local minimum on some open interval I containing the number C, so that for all x in this open interval, now all the y values leading up to the minimum are greater than that y value at C. This is called a local minimum. All right, and once again, what does that mean? And small little graph. So once again, I'll just say here's C. Actually, there's C. And now my graph looks something like this. And what we're saying is that this point, which is f of C, which is the lowest point, one of the lowest points on the graph, and that by definition, all of these y values, there's f of x, f of x, f of x, you get it, right? F of x. All of these y values are greater than f of C, because f of C is one of the lowest points on the graph, which means this would be a local minimum. That's it. And then you'd come back, f of x, all that lovely stuff. Okay. So that means, that's what it means to be a local max and local min. A local max means you are a high point on the graph. A local min means you are a low point on the graph. And you can have multiple maximums and minimums. All right. So for the next examples, it just says the numbers, if any, at which f has a local maximum, what are the local maximum values? So find the local max, find the local min. Okay. So look at the first graph, and we'll say, read it from left to right. And when we read it from left to right, we see that right here is going to be a local minimum. It is a low point on the graph. So this is a local minimum. And then, again, reading from left to right, we get to a high point on the graph. This is a local max. That's it. There's nothing to it. Just look for a high point and a low point on the graph. That's it. Okay. And then looking at the next graph, reading from left to right, we have that at -1, 0. This is a low point on the graph. So this is a local minimum. And then we have a high point on the graph. This is your local max. And then once more again, we have another local minimum. Can't get any easier than that, y'all. That's it. Okay, there is something I didn't explain or have a definition for, but let's say if I have a graph that does this. And there's only one high point for the whole graph. This is no longer a local max. This is called a absolute maximum. It is the only high point on the graph. Like, that's it. Okay, so that would be an absolute max. And of course, there also exists an absolute minimum. I'm sure you know what that looks like, but we can draw it. So let's say my graph went like this. At this point, the only low point would be a absolute minimum. Okay. All right. So those are maxes and mins, constants, increase, decrease, constants on symmetry. Yeehaw. Everything we need to know about a function. Let's keep going. All right, next is something called the average rate of change, which just is a fancy way to say slope. The average rate of change helps us find the slope between 2 points on a function. And the average rate of change is given by the change in y over the change of x, which in function notation is f of b minus f of a over b minus a. Now, we have seen this formula before, but never in function notation. This formula is the one we learned in, I'm going to say middle school, right? y2 minus y1 over x2 minus x1. Same exact formula. This is in coordinate notation. This is in function notation, because we are dealing with functions now. Okay. Nothing different. Just, I guess, looks a little scarier because it's not the notation we're used to. All right. And as well, what it helps us find, let's say I have my value of a here, my value of b here, and my function looks like this. Well, what the average rate of change helps us find, there's f of a and f of b. All the average rate of change does is helps us find the slope between these 2 points. We are looking for the slope or average rate of change. That's all it does. It finds the slope between 2 points. Okay, with that being said, let's find the average rate of change for the function 3x squared, given the x values 1 to 3. So label everything. A is 1, B is 3, and for my A rock, my average rate of change, I get f of 3 minus f of 1 over 3 minus 1. That's following the formula. F of b minus f of a over b minus a. Okay. And all we have to do is take 3, plug it into that function, take 1, and again plug it into that function, evaluate and simplify. So I'll write everything out. So f of 3 becomes 3 times 3 squared minus f of 1, which becomes 3 times 1 squared over 2. And then 3 times 3 squared, that's 9, that's 27, minus 3 over 2, and we get 24 over 2, which gives us 12. Okay, so once again, if you wanted a graphical representation of what you just did, well, 3x squared probably just looks like this, right? Everything looks like a parabola today, all right? Okay, so they gave us that we had an x value at 1, and we had an x value at 3. So if I go up, I'll just find that point. There's f of 3, which would also be 27. And right here is f of 1, which would be 3. And all we have just done is found the slope between these 2 points, which happens to be 12. All right, perfect. Okay, that's it. So let's do it again. 3 and then 12, 18, 27. Yeah. Okay. Yeah. Good. All right. What I was doing in my head was adding the slope because the y value when x is 1. So once again, like at f of 1, it was 3, and the y value at 3 was 27. And to get from here to here, if the rate of change was 12, I said 3 plus 12, which gave me 15. And then 15 plus 12 gave me 27. So just the rate of change between those 2 points. You don't need to do that. It's just a thought lingering in my head. But hey, it checks out. Okay, do it one more time, right? From 1 to 5. So label A, B. Find my A rock. F of 5 minus f of 1 over 5 minus 1. Write everything again. 3 times 5 squared minus 3 times 1 squared. Remember, we're still using the function above 3x squared over 4. And then you get 25 times 3, 75 minus 3 over 4. 72 over 4, and that is 18, right? 4 into 7 is 132, yep, 18. So all we're saying is that the average rate of change, or the slope from 1 to 5, is 18. It's increasing by 18 units. All right, that's not bad. That was fun. Okay. All right, last page. So we go over the definition of the secant line, which is the picture below. A secant line is a line that goes through 2 points on any function, right? It goes to 2 points on any function. Okay, and we can find the equation of a secant line if we know the slope between those 2 points. And that's it. Yeah, if you find the slope between those 2 points, then you'll have enough information to find the equation of the secant line that goes through those 2 points. So that's what we're going to be doing in the next example. And it just so happens that, well, the last page, we were finding the slope between 2 points, which is known as the average rate of change, right? If you want to find the slope between 2 points, that's known as the average rate of change, which can also be known as the slope of the secant line, because our next example is going to say find the slope of that secant line. So this is also the formula for the average rate of change. Nothing new. We're just going to be finding the equation of a line. And I'll show you how to do that. Okay, so we know how to find the slope between 2 points. Now we're going to use that information to find the equation of a line. So let's go ahead and do that down below. Find the equation of a secant line. So given the function 3x squared minus 2x plus 3, find the average rate of change of function g from -2 to 1. And then once we do that, we are going to find the actual secant line. We're going to find the equation of it. So first is the average rate of change. My A rock. All right. And again, label everything. Here's A, here's B, which means we're going to have G of B, which is 1, minus G of A, which is -2, over 1 minus -2. Okay. And now, take these values and plug them in to g of x for x. And I'm going to just use a calculator to make my life easy. And your life easy, right? All right, let's see. 3x squared minus 2x plus 3. And if I type in 1, I get 4. Minus, if I type in -2, I get 19. Over 1 minus -2, 3. This will give me -15 over 3, which gives me -5. Okay, so what we're saying is that the average rate of change from x equal -2 and x equal 1 is -5. This is also the slope of the secant line. M secant, slope of the secant. Okay. 2, find the equation of the secant line containing -2, g of -2, 1, and g of 1. Okay, so since the secant line is linear, we need to find a linear equation. So there are 2 ingredients to finding a linear equation. The first ingredient is we need a slope. The second ingredient is we need a point. Well, guess what? We already have points. It gave us 2 points here. And what can you find between 2 points? You can find slope. So we have everything we need. So let's go ahead and do that in step 2. 2. Let's try purple. Yeah. So first thing we need, well, actually, what I wrote down here, This is a special formula called the point slope formula. It helps you find the equation of a line. So let me write that down. Point slope formula is y minus y1 equal to m times x minus x1. And what's great about this formula is that it tells you what you need. You need a point and a slope, which we have. So my points that were given are -2 and g of -2 and 1 and g of 1. And we only need 1 point, but we need these points to be complete. Did we find g of -2 and did we find g of 1 already? And that answer is yes. They're right there, right? G of -2 is 19. So I have -2 and 19. G of 1 is 4. I have 1, 4. So once again, all I need is a point, and all I need is a slope. So we have 2 points. We have more than enough information we need, which means I go on to the next ingredient, which is the slope of the secant line, which we found above, and that's -5. We have our 2 ingredients, plug them in. All right. So when we do this, running out of space. Okay. Change color. Let's see. So it doesn't matter which point you choose. We're gonna get the same answer. So I'm gonna go with the easier point. We're gonna choose 1, 4. And I'm gonna say y minus my y1 value, which is 4. Equal to my slope, which we have is -5, times x minus the x1 value of that point, which is 1. All right, now solve for y. Y minus 4 equals -5x plus 5. Add that 4 over, and we get y equals -5x plus 9. This is the equation of the secant line. That's it. So actually, this is right. I was going to draw it for you, but since it's video, let me go show you this cool website that you can use since we are remote, right? There's this cool website called Desmos. And I have 3x squared minus 2x plus 3. So I'm going to type in the function we just had. So this is desmos.com. It's really awesome. Let me type in what we just had. 3x squared. Let's see. I am recording on this screen. Actually, I can probably make it smaller for now. You go there, and you go there. (3x squared minus 2x plus 3). Let me minimize myself there, and look at that. It graphs it for us over here. But now, I'm not worried about this graph. I want to make sure our secant line is correct. So now down below, I'll type in our secant line. Y equals -5x plus 9. And look at that. Now I'll maximize this screen. All right. No. How do I do? this. I just want that. Hang on. Technical difficulties. All right, I think I can push that to the side. There we go. Okay, better. So look at that. There's this point here, which we have as 1, 4. Did we not get 1, 4 as a point? We sure did. And then up here is another point, -2 and 19. Was that a point? It sure was. And since we had those 2 points in the function, and we found that the slope between these 2 points was changing by -5, we found the equation of the secant line, which goes straight through our parabola. And that is it. Ooh, okay. Till next time, y'all.